Hey there, this is Konstantin Schürholt with Ndea. If you're watching this, then you've probably heard about the Hierarchical Reasoning Model, a paper that got a lot of attention online recently. We got very interested in it as well because it performs well on ARC-AGI, the main benchmark that we're interested in. And we found some interesting things, so we decided we wanted to share it as well. So the main motivation of that work is to work towards reasoning. And they state that to get to reasoning, what reasoning basically is devising and executing complex goal-oriented action sequences. So they define reasoning as a sequences of actions that are on a division level and on an execution level towards a specific goal. To get there, they take inspiration from the brain in two ways. The first is that the brain processes signals at different frequencies. There are some areas in the brain that operate at lower frequencies, sort of more slowly, and some areas in the brain that operate at faster frequencies, so sort of more fast at higher frequencies. But these two influence each other. So the lower frequencies sort of guide the faster thinking of the faster frequency, higher frequency areas, and the output of the higher frequency thinking processes also influence the lower frequency, the slower thinking kind of processes. And so they thought that was interesting. The other component of the brain that they take inspiration from is recurrence. So basically, reasoning specifically is not just a forward pass. Sort of you get input, you think a bit, and then you have your reasoning trace. They claim there's recurrence in the brain. So you sort of iterate and refine as you go along. The main gap that they identify in previous work that they want to address is chain of thought kind of work. They say that it suffers from brittle task decomposition and high data and compute requirements. The other sort of less outspoken goal is that transformers don't scale well. Specifically, they don't scale well in low data regimes, which is what the ARC-AGI benchmark is all about, right? This is like very small amount of samples per task, very complex, very hard for deep learning methods to do. So on this kind of a domain, transformers don't scale well. And so I want to address that. So we'll take a look at the methods. We'll take a look at the main results, and then we'll dive a bit deeper and try to understand what makes this method work. Here are the links to the papers and to the code as well, their code, and we'll also have our code to reproduce the experiments that we've done. All right, so the method has basically 5 components to it, at least the way I see it. The first one is this iterative refinement, right? Taking the inspiration of the recurrence in the brain, they want to refine processes as they go along. Basically, you make a prediction, you don't stop there, you refine it until you're okay with it. This refinement happens on 3 levels. There's an outer refinement loop and 2 levels of an inner loop that are hierarchical. The general refinement is given a context and an initial guess, refine until you reach equilibrium or you're happy with it. The second component to all of the HRM model is the actual hierarchical model. This notion of a lower and a higher frequency in the forward passes, which basically means one component is called more often, the other component is called less often. So updates in one are faster or more frequent, and updates in the other are slower, less frequent. In the outer refinement loop, they also have a learned halt signal, which they call adaptive compute. Basically, learn the model to control the amount of refinement steps, the amount of time it takes to solve a specific task. Next component is the usage of task embeddings. So usually in problems like ARC, where you try from a set of training input and output pairs, try to understand what the transformation from input to output is that describes this particular task, this particular set of input-output pairs. You have training examples where you have access to the input-output pairs, and you have a test example where you only have the input and you're supposed to make the prediction to the output. So GPT-3 style for these kind of tasks is you show the training example and you ask the model to make a prediction for the test example, given that it has the future context of the training examples. They decide not to do that. Instead, they provide task embeddings where the task ID tells the model what the transformation is it's supposed to do. Quite an interesting choice. And then they also use data augmentations, the common, computer vision data augmentations, both to increase data set size for training, but also at inference time, so that they have basically several predictions across different augmentations, so they can do majority voting on it. Quite interesting. At a 10,000 foot level, this is what the entire approach looks like. So there's an outer loop around, in the center is the HRM model. Basically, if you start with a new task, you feed it into what they call a task carry that contains the actual task data, the input grid, and the task ID, the unique identifier that tells the model what task, what transformation it's supposed to work on right now. This task array also contains the number of steps that this task has already taken if you start at 0 and whether or not it's done with it, which they call halted. And it also contains the embeddings for the lower level and higher level hierarchical modules. So 2 types of embeddings, L embeddings, H embeddings. We'll keep talking about these. In the beginning, they are just randomly initialized. You feed all of this to your HRM model, and on a very high level, it does something with it. What it predicts is an output for this input. So input-output pairs. It gets the input, it predicts the output from the input and this ID. It also predicts whether or not it's done, so halted yes or no, as well as an update to this L and H embeddings. So these are fed in, and they also come out in a refined version. And so the outer loop is basically, unless I'm done or I've reached the maximum amount of steps that I'm allowed to take, I keep going. So this data here, the L and H embeddings, they override these, and then I just keep going. I just keep iterating over this until the halted signal is yes, or I've reached the maximum amount of steps. That's the outer refinement. The HRM model has 2 main components. That's the L module and the H module. And what comes into the entire HRM model are the inputs that are fed into some embedding module. We'll look at that too. So we have embeddings of the inputs. We have the ingoing H embeddings and the ingoing L embeddings. And what this does is basically updating the L and H embeddings sort of iteratively until it finally comes to a prediction for the entire input. So first, it updates the L embeddings by forward propagating the L embeddings and the current H embeddings to the L module. And with each L module call, it updates only the L embeddings. So this happens N times and L times. And then with these updated L embeddings, it also updates the H embeddings by passing both new L and original H embeddings to the H module, right? And then we have a new H embedding. And then we do the same thing again. With that new H embedding, we pass several times to the L module again to update the L embeddings a few times. You get the gist. So you basically, with a specific H embeddings, you update the L embeddings a few times. That's the faster paced thinking. And once you've done that, you also update the slower module, the H module, by updating the H embeddings. Now, the clue here is all these iterations happen without gradients. So this is just updating the latent state, these embeddings, the H and L embeddings. Once you've done that, once you're done with your hierarchical iterations over H and L, where the H module is supposed to be the slower guidance signal and the L module is supposed to be the faster thinking signal, then you do a final forward pass to both of these again. The H module takes the current state of H and L, which is updated after the L module. But this time you do that with the gradients. So in code, this looks like so. You iterate over these loops through L and then also through H without gradients. And then you take a final forward pass to your LNet to update the L state, to your HNet to update the H state. And that final H state is what you feed to a head. And that head gives you a final prediction, right? So iteratively refining towards equilibrium by sort of calling L a few times and then calling H, L a few times H, and then doing a final forward pass for a prediction. In my own sketchy drawing, it's like this. It's the same thing. It's just a different way. Maybe it helps some of you. You get some input embeddings from your embedding module. You have your ingoing H and L embeddings. You do this in a loop step without gradients. That's these iterations, the hierarchical iterations. You get a new H state and a new L state, or H embeddings, L embeddings. With all of this, you do a final forward pass to your L transformer. You get a new L state again, final forward pass to the H level transformer, a new H state again. And from that last ZH, the last H embeddings, and you feed those to a LM head and a Q head. The LM head gives you the final output prediction. So from that input, what is the predicted output? The Q head gives you basically the halting signal. Am I done? Am I not done? So yeah, there's a lot going on, but really it's just processing the input and updating some H and L embeddings to get this final prediction. Now, interestingly, these are not just wasted, right? Because you do this outer loop, because you might be wondering, like, why am I not throwing this away at this point? I'm done with it, right? You actually keep these as well, and you feed them in the next iteration, like back in here again. Okay, so one more finer point that I wanted to make here is these embedding layers, because I think they're particular, and I think they have an impact on the model performance as well. So I mentioned this up top. Commonly, for this kind of a problem, the models see context other examples for input-output pairs that describe this particular transformation, and then an input and ask the model to understand from the context what the transformation is, and then to apply it on this input. Like I mentioned before, they decided not to do that. So the input to the model is literally just one input example, so one grid. They pad it to 30 by 30 and then flatten it, so it's a sequence of 900 is basically color values. And then they also feed this puzzle identifier. And the puzzle identifier is composed of the unique task ID. So all input-output pairs of this task share this ID because it's the ID of the same task. But also what transformation and what color mapping have been applied to this particular version of this particular task. Because they apply augmentations, right? If you change the color, then the task is changed. So they encode this in this puzzle identifier. This puzzle identifier describes uniquely what specific task this input example belongs to. They feed the flattened color array to just a regular embedding layer. So, there are 10 different color values used in ARC. So it's basically one hot encoding each of these into like a 10 by hidden dim embedding layer. So what you get from this is basically a 900 by hidden dim array that comes out of it. So far, so straightforward. But the same applies for the puzzle embedding layer as well. So basically you have just not 10, you have like a large amount of different unique puzzle identifiers that you also, again, one hot encode and feed to a puzzle embedding layer. But this is quite big because the number of unique hashes that you have to understand, or like that the model has to understand, is the number of tasks that it can see, these unique task IDs, times the number of augmentations that you've applied per task. And this can get quite big. And crucially, this puzzle embedding layer, the output of it, or basically the puzzle identifier, this is the only information the model gets on what to do with this input, right? Several inputs, or the same input could belong to several tasks. So there's no unique information in the input of what to do with it. So to understand what to do with this input to predict the outputs, the model has to rely on this particular puzzle identifier. It's the only information that it gets. And as a consequence, because this is an embedding layer, right? It's fixed. It has this fixed amount of rows. You can probably extend it somehow, but generally it's a fixed size, and each row in it has a specific fixed meaning to it because it belongs to a fixed puzzle identifier. This model can only work on puzzle identifiers it has seen at training time, right? There's no way of like feeding in a new task with a new puzzle identifier and then trying to make an inference of it. The model wouldn't know what to do with it because it hasn't seen it at training time. Okay, taking a step back. HRM has an auto-refinement loop that tries to propose a solution, understand what it's done, and refine what it's not. And in the equilibrium loop, that's this hierarchical component that refines towards equilibrium when H and L level kind of agree with themselves. And it uses puzzle embeddings sort of as a way to learn how to associate a puzzle hash with a specific transformation, so it knows what to do with an input to arrive at the output. The way training is done has two components. It's a prediction loss and a Q-learning loss. Input-output, we've just seen this, right? The input is just the input grid and the puzzle identifier. The output is the prediction for this input and the puzzle identifier, as well as the halting or continued signal. The prediction loss trains for the output. It's just a supervised classification on a per token level. So for every token, it tries to encourage the model to make the correct prediction. Cross entropy, very standard. The Q-learning loss tries to learn this halting signal. It's also binary cross entropy on both the halting as well as the continue value. So it assigns two values to each possible state, possible action. Action 1 is halt, action 2 is continue. The halting target is basically, it's 1 if and only if your current prediction is correct, actually, and it's 0 otherwise. And the continue signal is, it's either the halt signal of the next step if the next step is the last step, or it's the maximum overhaul and continue of the next step. So fairly straightforward. Yeah, this looks complicated, really not. And this is also just very straightforward. So training is very straightforward, which is nice. For inference, it's also interesting because I think I already mentioned this as well up top. They use all the different augmented versions of the individual inputs that they have that they want to make inference for. So they don't just take the actual original one, they take the original and all augmented version of the same inputs. And they make predictions for all of them separately. So if you look at the figure here, if that was your original input, you could rotate it, you could mirror it, you could recolor it, you would get 3 different versions. You could make an inference for all of them, right? Because, your model has learned to deal with all of them. And then you would arrive at different predictions for the same task. And you can use the fact that these augmentations, these transformations, they're invertible. So you can map them back to the original task version, basically. And then you have different predictions for the same task, which is kind of neat because then you can basically check, is there one that comes up more often? And that's exactly what they do. They use majority voting on this pool of predictions with the same model. Very, very, very neat. One last note, at training time, they use this Q-learning signal, this sort of halting signal, but at inference times, they do not. So at inference time, they just always use the maximum number of auto refinement steps. This ACT is disabled. Okay, time for some results. Top level numbers. On ARC-AGI-1, the public score is 41%. We've reproduced these check out. The semi-private score on the semi-private dataset is 32%, pass at 2. So on V1, this puts the HRM model right about here on the landscape. It's a neighborhood of Claude Opus 4 in thinking 16K steps. Fairly performant, particularly given the fact that it only trains on the actual ARC data. There's no other pre-training going on. The cost per task comes out at relatively high, but again, this is because the model is actually trained. There's no pre-training going on. It just starts from random initialization. On V2, the public score is 4%, and the semi-private score is 2%. And that sort of checks out with the numbers that they put in the paper. So this is ARC-AGI V1, V2. They claim 40.3, so our numbers are a bit above that for V1, and they claim 5.0. Our numbers are below that. There's a bit of noise. It's to be expected. So the claim, the performance claim that they have in the paper is legit. Their method works really well. Next plot that they use in the paper, which I thought was interesting, both are concerned with scaling of models. To the left, it's accuracy on Sudoku Extreme full by scaling a transformer in parameters this time. So on the gray curve to the bottom, basically making the transformer bigger, you can tell that it doesn't really do anything if you scale it in width. So the depth of the transformer remains the same, just every layer gets a bit wider. But if you do scale the depth, so if you increase sort of the thinking steps, the amount of refinement that you do by going deeper, you do actually benefit in performance. The right plot is something very similar, only it's not the parameters on the x-axis, it's the depth. So the amount of transformer layers that you go through, in a sense, right? Because you can do that with the same curve as here. It's actually the same curve, even though it's not the same x-axis, comes out the same. Because here, if you add a layer to the right, then you also add parameters to the left, because that's the only way a regular transformer can sort of get deeper. But at some point it plateaus, right? Here too. But you can sort of feed the output of the transformer back into the transformer. At that point, you don't add more parameters. It's the same size model, but it computes more. It's this sort of refinement loop. If you do that with a recurrent transformer, this is the layer they show, you have a higher peak, you can compute deeper without plateauing, and their model sort of comes up here. So the claim that they make with that figure is compute depth helps you, but regular models can't do it, and their model can do it. Last plot on this line of thinking is, well, trying to make a case for why the hierarchical component is relevant and matters and should be there. Yeah, there's a lot going on. Well, I'll try to unfold it a bit, at least how I understand it. So on the y-axis is forward residual, on the x-axis is step. And they make the argument that recurrent neural networks, regular recurrent neural networks, as they do their refinement steps, they collapse. So they very, very quickly reach equilibrium and not much is going on anymore. So you can do refinement, you can do thinking steps, but after a few thinking steps, you basically don't benefit from it anymore. Deep neural nets, on the other hand, notice that the x-axis is like way, way higher than the step index here. They go off rails at some point. So while it does work to a certain degree, at some point there's just explosion of something, and that's not good either. And then their model is sort of nicely tuned in between because they have this H and L level forward residual. The H level, the lower frequency, higher level thinking kind of module, it goes down slowly, and the L level sort of in this iterations where each of these steps is when the H level is updated, it goes down slower. So you can do more thinking steps before you reach equilibrium and you don't update anything. That's their case for why the hierarchy is good. And then there's some, other than the top level numbers, there's some interesting qualitative results in the paper as well, where they look at basically the time steps, the outer refinement steps, what happens to the output. This is a maze where you can basically see how the trace of going from one spot to the other spot evolves until it's sort of convergence. actually continues. There's a gap here. It's gone there. Same for ARC, where this is one of the input-output examples for one task. And this is how it evolves for this test input, transforming it into the correct test output. Right? Note again that this is how you would commonly see this. You would give context and then give this test input, ask it to arrive here. But again, they don't show this. They just show the embedding of this bubble identifier. Okay, so it does work. It does reach high performance metrics on V1 specifically, ARC-AGI V1. So we wanted to understand why. There's a lot going on. What component of this drives the performance? So we identified a few candidates. It could be the model architecture, this HRM architecture with the hierarchical refinement. It could be the inner refinement loop, the parameterization of this. It could be the outer refinement loop, this outer loop with or without the ACT, this halting signal. It could be the data augmentation, because in the paper they use 1,000 augmentations per task, which seems a lot. But it could also be the puzzle embeddings. And so in the coming slides, I'll just basically walk through each of them and try to get closer to see what is it. First off, the architecture. Basically, does the HRM model matter in trying to reach the performance level that they reach? To get close to that, we compare the HRM model architecture. We replace the entire thing just with a regular transformer. It's matched in parameter count. Their model has basically 2 transformers, the H level and L level. They're both transformers. We just replace both of these with just one, but same parameter over parameter count. We keep all of the rest of the training pipeline the same. So they also use the same inputs, the same outputs, makes the same predictions, gets called in the outer refinement loop. So it's really just the HRM model that gets replaced. And we keep all of the rest of the hyperparameters the same as well. So we didn't optimize at all. We just literally replaced the architecture. One note here is that this transformer has the same parameters, but it has less forward compute specifically because it doesn't do these sort of search, refinement, equilibrium steps in the HRM model. So in the figure on the right, the parset 2 score on ARC-AGI V1 public, so it's reproducible, over the number of outer refinement loop steps. So these ACT outer loop steps. In blue are the HRM model scores, and in orange is our sort of drop-in replacement with the transformer. And these results are quite interesting because this unoptimized transformer always reaches within approximately 5% of the HRM model. There's a bit of variance for just one loop. They're basically the same. For 2 loops, the HRM model pulls away a bit. And then as we go up in more outer refinement loop steps, the gap closes a bit. We don't know if it would close all the way. We haven't run that experiment, but it does seem to close a bit. Also note that in these numbers, there's a bit of noise. So it could be a bit smaller, it could be a bit bigger, the gap. And that's interesting because that seems to tell us that it's not the HRM module that explains most of the performance. It does give a little bit of a boost, at least in the more outer loop steps, but it's not the main driver for the performance, at least not on ARC. Okay, so if it's not the architecture, is it maybe the inner loop that does make a difference? We basically, in this case, keep the HRM architecture and vary the number of cycles, L and H cycles. In their paper, they use both 2, and so we varied to 1, 1, 4, 4. We also tried to do 8, 8, and then run different variations. We stopped that at some point because 1, 1 already reached 7/8 of the performance, so it's within 4% of the 2, 2 cycles. So it, again, doesn't seem to make a huge difference. And then as you increase the number of these iterations, your compute cost goes up. So 2, 2 is already 4 times as expensive in runtime as 1, 1, and it just keeps exploding. We had to kill this job here just because it was too slow. It also doesn't really seem to matter that much. So in our hunt on understanding what matters, we just had to look elsewhere. And the next thing we looked at, and it already kind of showed on 2 slides ago, is the outer refinement loop and potentially the ACT. Does the outer refinement loop matter? We tested that by varying the max outer steps at training time, but in their baseline setup, that also varies the amount of outer loop steps at inference time. So if you set it to 1, then you'll do 1 step at training time and 1 step at inference time. If you set it to 4, you'll do 4, maximum 4 steps at training time and always 4 steps at inference time. In the figure at top is both of these together, right? Again, parset 2 on ARC-AGI V1 over the HRM model set with max steps 1, 2, 4, 8, 16 with ACT, with this adaptive compute enabled, or without, 16 without. And as you can tell, going from 1 loop, which is basically no refinements, to 2 loops, which is 1 refinement steps. You make a prediction and you get to change it once. Gets you from 19% to 32%. So a 13% jump in just 1 refinement step. And going from no refinement to 16 steps or 8 steps gets you to around 38 to 39%. Again, there's like noise in it. Sometimes it's 40, sometimes it's 41, sometimes it's 39. So it's basically twice the performance on Parset 2 and ARC-AGI-1. So these refinement steps make a huge difference, whereas the architecture and the hierarchy and the inner loop did not make a difference, not at least to that degree. The second component that is interesting is this halting signal. It does make a difference, but it's a very small one, right? So on ACT 16 loops, so 16 outer refinement loops max with ACT enabled versus 16 outer loops with ACT disabled, at least at training time, the gap is around 3%. So again, there's a difference, but it's not huge. The thing that really does seem to matter is that you do refinement. It doesn't matter that much if you control the compute that you actually invest in it. Just the refinement itself is the statement that matters here. Right. The next thing that we looked at is here again in their baseline settings, the refinement loop steps are the same for training and inference, right? So if I can take 4 maximum steps at training, I also take 4 at inference. And we want to understand, are these refinement steps more important at training time or more important at inference time, right? Because there's a case to be made that you maybe just train on a few refinement steps, but that at inference time, you really want to spend the compute there. And interestingly, that's not what we found. So here in this lower figure, we compare 2 models, 2 types of modules. The blue ones are the same bars as up here. If it's 1, then it's 1 refinement steps at training time, 1 refinement steps at inference time. If it's 8, it's 8 refinement steps at training time, 8 refinement steps at inference time. So blue means training and inference steps are the same. Orange bars are the module is trained with 16 refinement steps. So it's basically this bar here. And these two should be the same. There's noise, which is why they're not the same. And then on the x-axis value, he describes how many refinement steps do I take just at inference times. So again, all of these orange bars are trained with 16 refinement steps. And then inference happens with 16, 8, 4, and 1 refinement steps. So we can compare basically what's the impact of using the same amount of refinement steps at inference time, but training with different refinement steps. So here we compare 2 models that both use 1 refinement step, so no refinement basically, at inference time, but this one has been trained with 1 refinement steps and this one has been trained with 16 refinement steps. And it's curious because what we see is there's the smooth curve on training and refinement inference with the same amount of steps, and in orange, this curve is way flatter. So it does not suffer as much from using less compute at inference. Or in this example specifically, what this seems to show is if you train with refinement, you get better predictions without refinement, right? Apparently, if you learn to fix your errors, fix what it wasn't quite right in the previous iteration, your prediction is going to be better for it. So you don't have to refine it even at all. That explains to me anyways, this huge gap from training without refinement to training with refinement, but at inference time, not using refinement at all. But still, if you use refinement, you benefit a bit. There's a bit of a boost still. So yeah, a take-home message from this slide, refinement really makes a difference. It's this that drives the performance to the most part. The next component that we looked at is the amount of data augmentations. They use 1,000, which seems like a lot, specifically given that there are only about 1,000 data samples in ARC-AGI. So we want to understand, is that necessary? To what degree does it drive performance? Can we get away with less? Is it more important at training or is it more important at inference time? So we tried to vary the amount of data augmentations used, which was a bit complicated because of the way the model is designed. Your model can only deal with augmentation it has seen at training time, right? So for training, we can compile new datasets with a smaller amount of augmentations. That's not a problem. But at inference, we can't go larger than that, but we can go smaller than that. And the way we get around to that is we still do inference with all the different augmented versions of the same puzzle, the same input-output pair. But we randomly subsample from the prediction pool for majority voting. So we do majority voting not with all of the different versions, but with a random subsample of it. And that implicitly use less augmentations, right? Okay, what this shows is the number of augmentations used at inference time on the x-axis, on the y-axis again, Parset 2 on ARC-AGI-1 public. And the colors are different models that are trained with different amounts of data augmentations, right? So the blue one here is a model that has been trained with 300 data augmentations. And this curve that goes right down here is how does this blue model perform if you use less and less and less data augmentations, starting at 300 and going down all the way to basically just one example. And so, yeah, these are interesting effects because we see two things here. The first one is data augmentation clearly helps. So going from no data augmentation to using all the data augmentation, all the 1000 that they use, we didn't go higher than that, gives you a big jump from 15%. If you actually train without the data augmentation, this thing that doesn't show up on the plot, it's actually 10%. Yeah, it makes a huge difference, right? So data augmentation help. But what's interesting is that you don't need 1,000. 1% of it, so 10 data augmentations, which is this point here, gets you about 75% of the effect. So you get about almost close to 30% of V1 compared to the almost 40%. And if you use 30, so 3%, you get to almost 35. It's this magenta line. So data augmentations matter, but you don't need all that much of them. That's take home one. Take home two is, which is equally interesting, I think. As before, the data augmentations seem to matter more at training time than they matter at inference time. So it's more important for your model to be trained on different augmented versions than to actually use all the different augmented versions so that you have a bigger prediction pool and your majority voting somehow becomes more stable. It's actually not the case, right? Basically, the curves that start further to the right, so the curves of models that have used more data augmentations at training time, they are flatter. So as you use less and less and less and less data augmentation at inference time, they lose performance, but not as much. Whereas the curves that start further to the left, they decrease more steeply. So this particular one, the one that just uses 10 data augmentations, it just goes way below, right? Or we could just take this slice here, just compare what happens if I just use one example, or what happens if I just use 3 examples here. We see that using the same amount of budget at inference time, the amount of augmentations that I can use at inference time, models that are trained with more data augmentation just perform better. Yeah, these are the 2 points. They help. You need less than 1,000, but you still need like some, maybe 30, maybe 100. But you need them at training time. You don't need them as much as inference time. So inference could actually be cheaper because for every prediction that you're trying to make it 1,000 times. It might be okay to just do 30 of them. Okay, the last component, the puzzle embeddings. This is a bit of an odd one. We were trying to figure out if we could do ablations on it. We weren't able to do it ourselves, but we were in close conversations with the authors of the paper, who were incredibly gracious, very open, shared all the information they had. So kudos to them. What we learned from them and what we wanted to understand is what is the impact of the puzzle embeddings? So what is the impact of the fact that they use, this hash of this is this task with this augmentation and this color mapping, rather than showing the context of the other input-output pairs of the same task. They told us that they had run this ablation in a previous version of their code that used the context of other input-output pairs rather than the puzzle embeddings. And it's not quite the same state of code, so there's probably some performance improvements elsewhere at the same time. But back then, not using puzzle IDs, not using this puzzle embeddings, but rather using the context, they achieved about 76% of per token accuracy. And we tried to triangulate a bit. So we tried to look at other models, in this case, ablations over the number of data augmentations that achieved similar performance. So as you can tell, all of the bigger models at the end of training, they achieve well over 86% per token accuracy. But there's one model that early in training is maybe close to like 76%. It's, let's say around 78% of all accuracy, of per token accuracy. And if we look down where that comes out at parset 2 performance on public eval, that's well below 10%. So if we're generous and we say it's like around 10%, that's a huge drop from not using puzzle embeddings, showing the context below 10%, around 10%, maybe triangulated. This is a guess, right? This is not hard science. This is trying to get a signal, to using the puzzle embeddings. So that's very, very interesting. And we have a few candidates for potential explanations that we haven't tested at all. This is just basically sharing guesses, sharing potential leads for further experimentations. But yeah, there are several candidates of why this might make such a difference. The first one is the transformer gets a specific length of sequence that it has to deal with. The bigger that gets, the harder it is to learn anything from it. It's just more data to crunch through. That sequence length right now is 900 plus the puzzle embedding. If you were to give it 900 and then 900 for every other input and output of the task, that sequence is just way longer if you give context rather than puzzle embeddings. So using puzzle embeddings has a shorter sequence, might be easier to learn. The second thing is that puzzle ID gives you an extremely condensed signal. It's this task, right? Whereas if you have to extract that same signal from context, it's there, but you have to extract it. It's not as condensed. And as a consequence, it might just be significantly easier to learn how to deal with a puzzle embedding than to learn how to extract the same information from context. And that just may explain why it trains so well, specifically on low data regimes, because that's the other information that we got from the authors as well, which I thought was extremely interesting. They have run the same sort of ablation, but on ARC-like data sets with a lot more training data. And in these other regimes, same complexity, but significantly more data, showing context and then asking to solve a specific task, the usual few-shot learning way, performs really well. If you have enough data, it works really well. But in the ARC domain, where you have very little data, you're very data constrained, it doesn't work as well. So very interesting to see. All right, to summarize, as we come to a close here, we figured HRM is a very, very interesting submission. It has legit scores, it has high performance, specifically for the fact that it only trains on ARC. It doesn't pre-train on anything else. We found that the hierarchical component to all of this, the actual HRM model and the L loop and H loop, it doesn't matter that much. It makes a small difference, but it's not the main driver for this high performance. What really does make a difference is this outer refinement loop, the loop that makes a prediction and then iterates over it until it's happy with it. Similarly, data augmentation, very important, makes a significant difference, but not to the amount that proposed in the paper, significantly less. And specifically at training time, not so much at inference time, is where it makes a difference. The same goes for the refinement. Training time, very important. Inference time, not so much. And then we have this tentative signal out of conversations, not our own signal. Again, kudos to the authors. That the puzzle embeddings may be actually critical to learn efficiently on small data regimes, which is, again, very, very interesting. And that leads to a few questions for future work. The first one is what specifically is the impact of the puzzle idea? I would like to see somebody run this experiment and compare one-on-one so we have some hard data on this. Or is this maybe an extremely smart thing to do for low data regimes to just make learning easier? And the second thing is, how well does this entire pipeline, the HRM pipeline, generalize beyond its training data? It has to be trained on the data that it wants to evaluate on. Is there some way of fine-tuning HRM? As I understand it, the authors are currently working on this, so we'll see. Then ACT at inference time, the sort of adaptive compute at inference time, because right now they use always the max steps. At inference time, maybe there's value in halting, actually. I understand this is mostly a computational issue because it gets a bit of a mess if you hold some parts of your batch and then the rest are still to compute. So we'll see. Maybe there's some benefit in that. And then lastly, their approach is refining, but it's refining transductively. So it's on the actual prediction, on the data domain. You do a refinement until you're happy with it. And it'd be very interesting to see if a similar idea of refining, but not on the data domain, on the actual abstract program that does the transformation, works similarly. All right. Hope you took something away from it. And yeah, see you guys around.